Good morning students, I am T. Prasad, Assistant Professor, Department of ECE. I would like to discuss the combinational circuit design in DLCO. Let us see the design procedure for combinational logic circuits. Now, before going to see the basic design procedure of combinational logic circuits, let us discuss what is combinational logic circuit. Combinational logic circuit is a digital circuit whose output will always depend on the present inputs, and the output will never be depending on the previous outputs. And combinational logic circuits will never require any type of any external triggering circuit. So combinational logic circuits are built up of basic combinational logic elements. Clearly, the combinational logic elements are logic gates. Now let us see the basic procedure of combinational logic circuit. In the combinational logic circuit design, the first step is design statement. What is design statement? In a combinational logic circuit design, what circuit you are going to design? That is the design statement. Suppose if I am designing a multiplexer. Multiplexer is a logic circuit whose output will be one of the many number of inputs based on the combinations of two selection lines or n selection lines, where inputs are 2 power n inputs whose output is only one output. This output will be selected as per the combinations of two inputs, selection inputs. So like that, here design statement in that multiplexer design is design of multiplexer circuit, 4x1 multiplexer, let us say 4x1 mux. Or else if you are taking any arithmetic circuit like half adder or full adder or half subtractor or full subtractor, design of a half adder circuit, design of a full adder circuit, design of half subtractor circuit, design of a decoder circuit. Like that design statements will be there. So after design statement, next step will be design requirements. What is meant by design requirements for a logic circuit? So in the early stage, in the design statement, combinational logic circuit seems to be a black box which will do some logical operation based on the inputs, and it will give some output. So there will be definitely a relation between this output and input. So we are not at all bothering about the internal circuitry of this combinational logic circuit, what it will have inside. But we will look what are the number of inputs, what are the number of outputs. So that is the design requirements or design specifications. So in this number of inputs and number of outputs are the design requirements. Suppose consider a half adder circuit. Half adder circuit is a logical circuit, combinational logic circuit, which will add two binary inputs and produces two outputs as a sum and carry. So two inputs may be either A and B, and two outputs will be sum and carry, S and C out. So these two inputs may not be specifically A and B only. You can name it as your own letters like X and Y or P, Q, like that. So number of inputs and number of outputs must be very clear while designing a combinational logic circuits, and we have to name them like A, B, C, and sum and carry. So after that, design description. What is meant by design description? It is the functional behavior of a logic circuit which will describe the relation between output and input. Suppose if you are designing a half adder, what may be the outputs of sum and carry with respect to the number of input combinations of A and B. That is the design description. Yes. Now after design description, there will be definitely relation between outputs and inputs. So we have to write the relation of outputs with respect to the inputs in terms of Boolean expressions. So in this Boolean expressions deduction, we can depend on K-map technique. K-map technique is a graphical technique which we will use to optimize the Boolean expression of any combinational or sequential logic circuits. So after that, Boolean expressions optimization based on the relation of the outputs with respect to the inputs. Next, logic diagram. So this is the basic fundamental procedure of the combinational logic circuits. Now let us review the total procedure of the combinational logic circuit as the design statement, design requirements like number of inputs and number of outputs, design description, Boolean expression optimization and logic diagram. Now let us review the design procedure of the combinational logic circuit, design statement, design requirements like number of inputs and number of outputs for a combinational logic circuit and the relation in terms of design description. And after that we have to reduce the Boolean expressions with the help of K-map technique or normal optimization techniques, and then we have to draw the logic diagram, which is the internal logic diagram present in our design. So this is a basic design procedure of the combinational logic circuit. Now let us discuss the entire design procedure with the examples of arithmetic circuits, half adder and full adder and their optimizations, and then we will draw the logic diagrams and we will verify the functionality both in logically and with the truth table also. Now let us design a half adder circuit. I already told you about the half adder design circuit. Half adder is a combinational logic circuit that will have two number of inputs and two outputs, which will add two binary bits of information and produces sum and carry as the output. So here I already told you the design statement seems to be a black box, half adder, whose number of inputs are 2 and number of outputs are 2, sum and cout. So now in our design of this half adder circuit, first design statement is design of half adder. Next statement, design step is number of inputs are 2, and also outputs are 2. So name those two inputs as per the designer wish, like A and B are the inputs and we have sum and carry, cout. So as designated above. So here now the third step is a very important step that describes the functional behavior of a logic circuit. Functional behavior of a logic circuit is nothing but design description. Design description tells the relation between the output and input. So we have a truth table in a digital logic circuits which describes the functionality in terms of Boolean values like zeros and ones. So here the truth table of an half adder is A and B are the inputs, sum and cout are the outputs. So here A and B are the two inputs. So we will be having, if n number of inputs are 2, definitely we will have 2 power n input combinations will be there. So 2 inputs will give you 4 number of input combinations, 0, 0, 0 and 1, 1 and 0, 1 and 1. So here the sum is the addition of 2 inputs, 0 plus 0. We will get sum as 0. We are not getting any carry. So here 0 is the output. 0 plus 1, Boolean expression for this 0 plus 1, sum will be 1 and carry will be 0. No carry is there. 1 plus 0, sum will be 1 and no carry will be there. So here 1 plus 1. So here 1 plus 1 is equal to 2 in decimal. But in decimal, for representation of 2, we will be representing the decimal value of 2 in binary with 1 0. So in this 1 0, 0 is the sum and cout carry will be the 1. It will be propagated to the next stage in multi-level adder circuits. So sum will be 0 and carry will be 1. So this is the truth table of the half adder circuit. So it is the description of the function of a half adder circuit. That means here if I am applying 0 1, output sum will be 1 and carry will be 0. If I am applying 1 1 as the input, the output will be sum will be 0 and carry will be 1. So this is the functional behavior of the internal circuit of the half adder circuit that will give sum and carry as the input for the input combinations of AB. This is the basic functionality of a half adder circuit. So in the design of any combinational circuit, if we are designing some combinational circuit, we should know the functionality of that circuit very clearly. Otherwise, we will never be describing the functionality in terms of the truth table effectively. If we are unable to describe the functionality of the truth table effectively, definitely it leads to the malfunction circuit design. So circuit functionality will be deviated from its originality. So this is the basic drawback if we are not having awareness over the design of any combinational logic circuits. If we don't have any awareness over the functionality of the circuit, definitely it leads to the faulty circuit design. So we should be very cautious while designing any circuit. So before going to design that logic circuitry for the combination circuit or sequential circuit, we should be having some clear idea about the its functionality, original operation of that circuit. Now the fourth step is Boolean expressions deductions. So here coming to this half adder circuit, definitely we have only two inputs and two outputs. So output, yes, sum is equal to, so if we are describing this input combinations in the format of decimal format, in the decimal format it is equivalent to 0, 1, 2 and 3. So we will represent this sum. The sum is 1 when the input combination is equal to 1. The sum is 1 when the input combination is 2. So S is equal to, sum will be written as the sigma m of 1, 2. Now Cout is equal to sigma m of 3. So these are the Boolean expressions in terms of sum of products, and we can also write these Boolean expressions in terms of product of sums also. So here sum of products, product terms will be generated and they are added to generate the Boolean expression. So each product term, this is 1. Let us for example 1 product term is A is 0, B is 1. So A bar B plus 2 equivalent is 1 and 0. A is 1 and B is 0. So A B bar. So sum is equal to A bar B plus A B bar. So this is the expression I have written by just looking into the output expression with respect to the input combinations. So as it is a simple truth table, I can easily write this. And if we are writing the same Boolean expressions for carry out, Cout is equal to, Cout is equal to 1 for the input combinations of 1, 1. So A is 1, B is 1. So A and B, AB. So if it is 0, this input literal will be complemented. So A bar B, like that. So if a input combination is equivalent to 1, it will not be the literal corresponding to that particular digit will not be complemented. And if it is 0, the input literal corresponding to that particular input will be complemented. So this is the simple notation to represent the Boolean expressions when the truth table is very simple. So if the truth table is having a more number of input combinations and more number of output combinations, and the outputs will be represented in terms of more number of input combination literals, then definitely we have to go for an optimization technique, which was very famous in digital circuit design, that is K-map technique. It's a graphical algorithm which is used to optimize the Boolean expressions of the logic circuits. So Cout is equal to 1 and 1. So definitely A and B. So this is the Boolean expressions detection. Later, the fifth step is, now after reducing the Boolean expressions, the last step of the combinational logic circuit is logic diagram representation. So logic diagram, I already told you in the beginning, the logic diagram, internal diagram of the circuit that we are willing to design will contain the circuitry in terms of logic gates. So coming to this Boolean expressions, S is equal to A bar B and A B bar. So A bar B and A B bar, it's a famous known equation, that is sum is equal to A XOR operation of B. Cout is equal to A and B. So just I am rewriting the optimized Boolean expressions in terms of standard logic gates. So these logic gates are available to us in the form of basic logic gates and universal logic gates. So here basic logic gates, XOR and OR NOT gates, XOR and XNOR, NAND and NOR gates will be there. So NAND and NOR gates are the universal logic gates. So I'm going to draw the logic circuitry of this design in terms of standard logic gates, A XOR B. So this is A and this is B. This is equal to sum, whatever it is. Now I'm representing Cout. A and this is B and this is AND operation. So this is Cout. Now this is A and B. Now this black box is this one. So internal logic diagram is this one. In this way we can design the half adder circuit with the help of a combinational logic circuit design procedure. Now this is the internal logic diagram that can be designed for a black box, what we have assumed earlier as a half adder circuit. So by applying input, any one of the input combinations of 1 and 0 as the inputs, 1 and 0 output is, for an XOR gate inputs, if A is 1 and B is 0, output is equivalent to 1, as we have seen from the truth table of the XOR gate. And for the 1 0 input combination for an AND gate, 1 0, the logic output is 0. So sum is 1 and carry is the 0. So sum is 1 and carry is the 0. So this is the functional verification of the functionality of the half adder circuit from the circuit diagram, not from the truth table. So this is the way of designing the combinational logic circuit for a simple half adder circuit. Now let us see the same combinational logic circuit design procedure for a full adder circuit. So now my design statement will be design of full adder. So full adder means, as I told you previously, we should know the functionality of the circuit which is to be designed. So full adder is a logic circuit used to add 3 inputs of information. So 3 binary inputs. So number of inputs are 3, number of outputs are 2, sum and carry. We can designate A, B, C as the input or else X, Y, Z. So this is the functional description of the full adder circuit. That is truth table of the full adder circuit, which gives the relation between sum and carry and the inputs A, B, C. So here, if you see, sum is equal to 1 for the input combination of 0, 0, 1, 0, 1, 0, 1, 0, 0 and 1, 1, 1. In the similar way, carry is 1 for the input combinations of 0, 1, 1, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So I have written the sum and carry in terms of ABC with the help of min terms, which are designated in decimal equivalent value from 0 to 7. So wherever 1 is there at sum, I have written as 1, 2, 4, 7 as the min terms, which corresponding to the sum expression equivalent to V1. And carry expression Cout is equal to the combination of min terms of 3, 5, 6, 7, where the output is equivalent to V1 with respect to the input combinations. So I mapped these min terms in a K-map technique. So this is the Boolean expression deduction step where I have applied K-map technique as the number of inputs are more compared to the half adder. So I mapped the min terms 0, 1, 2, 3, 4, 5, 6, 7. So in K-map, if adjacency is there, 1, 1 adjacency is there, I will group them as 2 adjacency, 2 min terms adjacency. But here no other min term is neighborhood of the other min term. So each and every one will have no adjacency in the graphical representation of a K-map. So I have taken as a singular coverage elements. So for this element, I have written the expression corresponding to this horizontal axis and vertical axis. So for this horizontal axis, A bar. For vertical axis, B bar and C. So this is 0 and this is 1. So B bar and C. For the next min term 1, A bar, B, C bar. For the next min term, this is corresponding to the horizontal row of this one 1. So A, this is equivalent to 0, 0, B bar, C bar. In the similar way, for the last min term of singular coverage, A, B, C. So this is A, B, C. So from this 2 product terms, I have taken A bar as common. So B bar C plus B C bar is the remained min terms, plus A as common from this above 2. So A is common means B bar C bar plus B C. So if you look at this expression B bar C plus B C bar, it is equivalent to B XOR C. If you see B bar C bar plus B C, it is equivalent of B XOR C. Suppose if I am assuming B XOR C as P, B XOR C is the complement of this B XOR C. So B XOR C is equivalent to P bar. So now this final expression seems to be A bar P plus A P bar. So it is equivalent to A XOR P. What is P? B XOR C. So A XOR B XOR C. So in the similar way, for Cout expression, min terms are 3, 5, 6, 7. So 0, 1, 2, 3, this one, 4, 5, this one, 6, 7. So I have mapped like this. So in this K-map, in this particular case, definitely there is a one coverage of adjacency. So 2 min terms are adjacent to each other. This one is the 2 min terms are adjacent to each other. For this vertical row, 2 min terms are adjacent to each other. So like that I grouped them as a covered min terms. So for the first coverage, this is corresponding to this horizontal row of A, and this is BC, 0, 1 and 1, 1. So C is constant, but B is changing. So I am neglecting this B. So C, A and C is the product term. In the similar way, for this coverage, I have taken A, and this coverage is corresponding to this column and this column. So 1, 1 and 1, 0. So 1, 0 is changing, so it is cancelled. So 1 is common, so B is common, so I have taken AB. In the similar way, this is another coverage adjacency, so it is equivalent to BC. So total expression is AB plus BC plus AC. In this way, I have reduced the equation for this Cout, and I draw the Boolean expression in terms of logic diagram, and I applied 1 0 1, so I got the 0 and 1 as the output with respect to the truth table. In this way I can design the full adder circuit. In the similar way we can also designing the remaining combinational logic circuits with this procedure effectively by using K-map technique to verify the functionality of the combinational logic circuits.